8, 7, 6, 5, 4, 3, 2, 1, and liftoff of Space Shuttle Atlantis, a final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Hello and welcome. This is the lecture number 2 in the chapter Motion in a Straight Line. In the last lecture in chapter Motion in a Straight Line, we have learned about the position and displacement of a moving object. We have learned about its average velocity and average speed. We have learned about its instantaneous velocity and speed, and we have learned about its acceleration. The key objectives of this lecture are to learn about the special case of accelerated motion, that is uniformly accelerated motion, and to learn about the relative velocity between two objects. The first topic for today is uniformly accelerated motion, which is a special case for accelerated motion. In uniformly accelerated motion, acceleration is constant with respect to time. Since acceleration is derivative of velocity with respect to time, the velocity is linearly varying, and since the velocity is derivative of position with respect to time, position changes quadratically with respect to time. So in a uniformly accelerated motion, acceleration A is a constant. Now we derive the basic equations of motion for constant acceleration case. First we determine the velocity. Since acceleration is constant, instantaneous acceleration is equal to the average acceleration, which is given by change in velocity v minus v0 divided by time interval t minus t0. In this case we have taken t0 to be 0. This gives instantaneous velocity as v0 plus at, where v0 is the initial time. This is the first equation of motion. After that we determine the average velocity. Since velocity is linearly varying, we can find the average velocity as the average of instantaneous velocity and the initial velocity. This gives average velocity as half of v0 plus at plus v0. This gives average velocity as v0 plus half of at. Next we determine the position of the object. We know that the average velocity of the object is the displacement divided by time interval. The displacement is x minus x0 and time interval is t minus 0. This gives the position, instantaneous position of the object as x0 plus average velocity times t. We have already obtained the equation for average velocity. Using that equation here, we get x is equal to x0 plus v0 plus half at times t. This gives x is equal to x0 plus v0 t plus half at square. This is the second basic equation of motion for the uniformly accelerated case. Eliminating t between equations 1 and 2, we get v square is equal to v0 square plus 2ax minus x0. This is the third basic equation in the uniformly accelerated case. So we have derived three equations for the uniformly accelerated case. V is equal to v0 plus at, x is equal to x0 plus v0 t plus half at square, v square is equal to v0 square plus 2ax minus x0. These three equations can be used to solve any problem for the uniformly accelerated case. Now what are the sign conventions used to solve any problem in linear motion? When the object is moving in the positive x direction, we say that the displacement is positive and velocity is positive. And if the velocity is increasing, we say that acceleration is positive, and if the velocity is reducing, we say that the acceleration is negative. When the motion is in negative x direction, we say that the displacement and velocity is negative, and if the magnitude of the velocity is increasing, we say that the acceleration is negative, and if the magnitude of velocity is reducing, we say that the acceleration is positive. When the object is moving in vertical direction, we use the following sign conventions. Upward motion is taken as positive and downward motion is taken as negative. Therefore, when the object is moving upward, the displacement is positive and the velocity is positive, and when the object is moving downward, the displacement is negative and the velocity is also negative. If only gravity is acting on the body, the gravity is always negative. That is g is equal to minus 9.8 meter per second square. This is also called free fall acceleration. Now let us take few examples. In this example, an object is dropped from a height of 50 meters. We are required to find how long will it take to reach the ground. So we are given that the initial position of the object x0 is equal to 50 meters. We are given that the final position of the object x is equal to 0 meters, that is the ground level, and we are given that the initial velocity of the object v is equal to 0 because it is just dropped from the height. The acceleration in the object is due to gravity only, therefore a is equal to minus 9.8 meter per second square. Using this equation, x is equal to x0 plus v0t plus half at square, and putting all these values in this equation, we get 0 is equal to 50 plus 0t minus half 9.8 t square. This gives t square is equal to 100 by 9.8 equal to 10.2. This gives t is equal to 3.2 seconds. Therefore, it takes 3.2 seconds for the object to fall to the ground. We can also calculate the velocity of the object just before hitting the ground, and we will use this equation v is equal to v0 plus at to obtain the final velocity. We know that the value of v0 and we have just calculated the value of t. This gives v is equal to 0 minus 9.8 times 3.2 equal to minus 31.4 meter per second. Therefore, velocity of the object just before hitting the ground is equal to minus 31.4 meter per second. In this example, an object is thrown upwards at a speed of 20 meters per second. We are required to find how high it will go before starting to fall down. We can take the initial position of the object as x0 equal to 0. The initial velocity of the object v0 is equal to 20 meters per second. Since at the maximum height velocity is 0, therefore the final velocity of the object v is equal to 0 meter per second. The acceleration is due to gravity only, therefore a is equal to minus 9.8 meters per second square. We use this relation v square is equal to v0 square plus 2ax minus x0. Putting all the known values here, we get 0 is equal to 20 square minus 2 into 9.8 times x minus 0. This gives 19.6, x is equal to 400, and this gives x is equal to 20.4 meters. Therefore, the object will go up to a height of 20.4 meters before starting to fall down. We can also calculate the time it takes to reach that height, and we use this relation v is equal to v0 plus at to obtain that value. We know that it is 0 meter per second. By initial velocity, we also know that it is 20 meter per second. Therefore, putting these values in this equation, we get 0 is equal to 20 minus 9.8 t. This gives t approximately equal to 2.0 seconds. In this third example, an object is thrown upwards from the edge of the top of a building of 50 meter height at a speed of 20 meters per second. The object goes up and then falls down to the ground. We are required to find how high it goes and how long it takes to fall to the ground. For this problem, we will take g equals to minus 10 meters per second square. When the object is going upward, initial position x0 is equal to 50 meters. This is the height of the building. Initial velocity is equal to 20 meters per second, and the final velocity, that is the velocity at the maximum height, is 0 meters per second. The acceleration is minus 10 meters per second square. Using this equation, v square is equal to v0 square plus 2ax minus x0. We get 0 is equal to 20 square minus 2 into 10 into x minus 50. This gives 20 into x minus 50 is equal to 400, and this gives x minus 50 equals to 20, and this gives x is equal to 70 meters. Therefore, this object goes to a height of 70 meters from the ground before starting to fall down. Using the equation v is equal to v0 plus at to obtain the time the object takes to reach the highest point. Since v0 is 20 and v is 0, we get 0 is equal to 20 minus 10t, and t is equal to 2 seconds. Therefore, this object goes upwards for 2 seconds. When the object is coming down, the initial position of the object is the maximum height it goes before starting to fall down. Therefore, x0 is equal to 70 meters. The final position x is the ground level, that is 0 meters. The initial velocity is the velocity at the maximum height, that is 0 meters per second. Using this relation, x is equal to x0 plus v0 t plus half at square, and putting these values in this equation, we get 0 is equal to 70 minus half into 10t square. This gives 5t square equals to 70, and this gives t is equal to 3.74 seconds. Therefore, the maximum height of the object is 70 meters. It takes 2 seconds to reach the maximum height and another 3.74 seconds to fall down. Therefore, the total time the object stays in the air is equal to 2 plus 3.74 seconds equals to 5.74 seconds. The last topic of this chapter is relative velocity. Suppose that cars A and B are moving on a straight road at a velocity of 50 km per hour. This is the velocity of the car as measured by an observer standing on the ground. For observer sitting in car A, car B is not moving with respect to themselves. That is, for observer sitting in car A, car B is stationary. Similarly, for observer sitting in car B, car A is stationary. We say that the relative velocity of car A with respect to B is 0 km per hour, and relative velocity of car B with respect to car A is also 0 km per hour. Now suppose that car B is moving at 30 km per hour. In this case, car A will move ahead of car B. The observer sitting in car A will see that car B is moving backwards. If he calculates the velocity of the car B, he will find that its velocity is minus 20 km per hour. For an observer sitting in car B, car A moves ahead. Therefore, for an observer sitting in car B, the car A is having a positive velocity of 20 km per hour. Thus, we say that the relative velocity of A with respect to B is given by velocity of A minus velocity of B. This is equal to 20 km per hour. And the relative velocity of car B with respect to car A is given by velocity of car B minus velocity of car A, and this is equal to minus 20 kilometers per hour. For better understanding, let us take an example. In this example, two trains A and B are moving on parallel tracks. Train A moves in negative x direction at a speed of 54 km per hour. Train B moves in positive x direction at a speed of 90 km per hour. We are required to find first velocity of B with respect to A, second velocity of ground with respect to B, and third velocity of a man walking inside the train A at a velocity of 5 km per hour with respect to train A as observed by the man standing on the ground. So we are given that the velocity of train A is minus 54 km per hour since train A is moving in negative x direction. Velocity of train B is 90 km per hour. Ground is stationary, therefore Vg is equal to 0 km per hour. And we are given that the velocity of the man inside the train relative to the train is 5 km per hour. So we can calculate velocity of train B with respect to train A as velocity of B minus velocity of A. This is equal to 90 minus 54 km per hour. This gives relative velocity of B with respect to A as 144 km per hour. Now the velocity of the ground with respect to train B calculated as VGB equals to VG minus VA. Since VG is 0 and V is 90, we get VGB is equal to minus 90 km per hour. We are given that the velocity of the man inside the train with respect to the train is 5 km per hour. The VMA is equal to 5 km per hour, and we also know that VMA is equal to VM minus VA. That means velocity of man with respect to train A is equal to velocity of man minus velocity of the train A. This means that Vm is equal to Vma plus Va. This means Vm is equal to 5 plus 54 km per hour. This means that Vm is equal to 59 km per hour. Therefore, velocity of the man with respect to the ground is equal to 59 km per hour.